Chem activity number 8 and in the corresponding videos, we will investigate how we can use nuclear magnetic resonance spectroscopy to determine the structure of an organic compound. Of the three techniques that we'll be looking at, that is mass spectrometry, infrared spectroscopy, nuclear magnetic resonance spectroscopy is the most powerful. It allows a chemist to precisely determine the minute aspects of an organic structure. We will focus mainly on Proton Nmr, but one could also look at C13 Nmr and phosphorus 31 Nmr. We will focus mainly on simple organic compounds, but this technique has also been applied to large macromolecules such as proteins. And this technique is related to the diagnostic tool of magnetic resonance imaging. This technique involves using nuclides with an odd number of nuclear particles. So as mentioned, we'll be looking at Proton Nmr. The most common isotope of the hydrogen atom has 1 proton and 0 neutrons, therefore an odd number of nuclear particles. We also mentioned that there's C13 Nmr, so while there's an even number of protons, so 6 protons, there's an odd number of neutrons in C13 isotope, therefore the nuclide would be considered to have an odd number. In the diagram on the left, consider that we have protons in an organic structure, and in space, these protons would be arranged in a variety of ways. And picture that each proton has a spin, something similar to the spin that's on an electron. And the spin would induce a small magnetic field. Now, because these protons are arranged in a random manner, the small magnetic fields would also be arranged in a random way. This is under the condition of no applied magnetic field. Assume that our sample is then subjected to an external magnetic field, which is represented by B0. And note that the external magnetic field in our diagram is pointing upwards. As it turns out, some of our protons would be aligned with the magnetic field, and so we'd say that those are in the alpha spin state. Some would be aligned against our external magnetic field, and so we would call that the beta spin state. The beta spin state protons would be of higher energy, but only slightly. So for instance, we might expect that 51% of the protons would be in the alpha spin state and 49 in the beta spin state. There's only a small difference in energy between these two states. In nuclear magnetic resonance spectroscopy, the idea then is in this external magnetic field, we'll apply energy that will allow the protons in the alpha spin state to flip to the beta spin state. This energy, as we shall see, occurs in the radio frequency part of the electromagnetic spectrum. That energy is sufficient to promote the nuclide from the alpha to the beta state. Now, all of this would not be particularly helpful if all our protons required the same amount of energy to flip from the alpha to the beta spin state. But as it turns out, the exact radio frequency required depends on the effective magnetic field. So while there's one external magnetic field, the effective magnetic field depends on the environment that each proton finds itself in. The environment will be related to whether or not it's a CH3 group or a CH2 group, or whether or not the CH2 group is next to an electron withdrawing carbonyl group. Those things will impact the sorts of environment that the protons find themselves in. As a bit of a schematic, this cartoon roughly reflects what a nuclear magnetic resonance spectrum would look like. So the intensity has to do with the number of protons that are in that particular environment. If we look at the signal on the right, we call these shielded nuclei in the sense that the protons sense a smaller effective magnetic field. This is because they're in an environment where somehow that magnetic field, that is, the external magnetic field, is somewhat shielded. And I'll explain in a minute how it can be shielded. Therefore, the energy difference between the alpha and the beta state will be relatively smaller. Therefore, a smaller frequency would be required to cause the protons in the alpha spin state to flip to the beta spin state. We call that flipping, in a sense, to come into resonance. By contrast, the protons that are found downfield, these protons sense a larger effective magnetic field. So it's always the same external magnetic field, but these protons are what we refer to as being somewhat de-shielded. Somehow they sense a larger effective magnetic field. Therefore, a larger energy will be required for that flip from the alpha spin state to the beta spin state. Now we'll come back to this diagram in a minute. I'd like to show you a simple but an actual nuclear magnetic resonance spectrum. And this has to do with this simple haloalkane, the structure that's provided right here. And as it turns out, that structure has two proton environments. The two proton environments we can show by labeling in the following way. So right here, this is one proton environment I'm labeling as A, and then these other CH3 groups represent another proton environment. We'd say that the protons that correspond to proton A are more de-shielded, and therefore they're found right here in our NMR spectrum. That single peak represents those particular protons. Now, why are they somewhat de-shielded? Well, they're somewhat de-shielded because they are right next to a relatively electron withdrawing group. An electron withdrawing group helps de-shield, or will de-shield, a proton environment. So one of the main messages will be the following. Electron density about an atom is shielding, and so if the atom is next to an electron withdrawing group, then that electron density is somewhat removed, and therefore it is somewhat de-shielded. By contrast, the protons that are in the methyl group are not near, or not directly near, the electron withdrawing group. Therefore, they are still relatively shielded. Essentially, they have a fair amount of electron density in their region. Therefore, they're found in this region of our spectrum. You'll notice that the x-axis is shown as a chemical shift. So this can be thought of as different radio frequencies required to cause the flip from the alpha to the beta state, or for the protons to come in resonance. Why is not shown as an absolute value is because different NMR instruments use different size magnets, will therefore require different radio frequencies to have the shift from the alpha to the beta state. In order for chemists to be able to compare spectra done on different NMR instruments, this is shown as a relative ratio compared to the operating frequency. The operating frequency will depend on the size of the magnet used in the NMR. Again, in order for NMR from different instruments to be compared, there's a standard that's used. Now, nowadays, the instrument actually doesn't require a standard to actually be put into the instrument, but rather it's done electronically. But in the early days, this standard actually had to be included. Now, how does this standard work? Well, notice that you've got methyl groups attached to a silicon. Now, silicon has an electronegativity of around 1.9. whereas a carbon has electronegativity around 2.5. So actually the carbon is more electronegative. So I'm going to go delta negative here, delta negative, delta negative, and the silicon will be delta positive. The environment around those methyl groups, therefore, has a large electron density. So we'd say those methyl groups are extremely shielded. And therefore, it makes sense that we'll set that to be our zero radio frequency. There are very few organic structures that would have a more shielded environment. And so compared to that, our other methyl groups, which are shown right here, are somewhat de-shielded because they're not bonded to something that is even less electronegative. So in this particular spectrum, You can see that it's relatively simple and it corresponds to two distinct environments. Now there are other features of the spectrum, such as the fact that there are single peaks, the fact that you've got this line that goes through like this, and we'll explain all of those features later. But for now, I'd like you to start to get familiar with the idea of the different proton environments. But let's just go back to our little cartoon here for a minute. So we explained that we had our shielded nuclei. So of course, our shielded nuclei would correspond, in terms of the structure that we just looked at, the CH3, the CH3, and the CH3. Whereas our deshielded nuclei would be the CH2 next to the bromine. So this again is what we mean by shielded versus deshielded. Now I realize that these terms here, upfield and downfield, can be a little bit confusing, and this has more to do with an historical convention. So we say that protons that are in a deshielded environment are shifted downfield.